Assalamualaikum warahmatullahi wabarakatuh. My name is Syam Mufallah Bakta Bishfar Bakatal, and in this video, we will talk about our group project, which is the application of numerical in civil engineering area. And for our project, our scope is more to drain. We will calculate the discharge water from the area that we calculate from the Simpson rule. And this is our group member. First of all, Yasmi Raihana, Alia Natasha, Alifa Inshira, Ishraf Nairuddin, and myself, Syam Mufallah Bakta Bishfar Bakatal. And now I will pass it to our first presenter. We talk about the introduction.
Assalamualaikum, my name is Nur Ali Natasha. Today, my group project will be presenting our numerical methods project. I'll be starting things off with the background, our problem statement, and our main project objectives. To give you some context, we decided to look at our urban stormwater management, which is a massive priority for preventing flash floods in rapidly growing areas like right here in Pahit Raja. Concrete monsoon drains are the main infrastructure used to carry large amounts of rainwater away safely during heavy downpours. As civil engineers, to design these drains properly, we need to know two main things: the cross-sectional area of the water and the maximum flow rate it can handle before spilling over. Now, because our drain is trapezoidal, the top width gets wider as the water gets deeper. This means we can't just use a simple length times width geometric formula. Instead of doing long, complicated analytical calculus by hand, we use numerical methods, specifically Simpson's 1/3 rule, to easily break the depth down into segments and calculate the area accurately. Moving on to our problem statement, in real-world fieldwork, we rarely get perfect mathematical formulas to describe a drain's shape. Instead, we usually just get stable or raw numbers measured at specific depths. This leaves us with two main challenges. First, because the width of this monsoon drain changes continually with the water depth, we need a reliable numerical method that can handle this changing geometry smoothly without overcomplicating the math. Second, to prevent flooding in the surrounding neighborhood, we have to know the exact point where the drain will overflow. Without linking the physical size of the drain to Manning's equation to find the maximum discharge rate, we won't know if the structure is actually safe during extreme weather. To solve this, our group set up a Simpson's 1/3 grid, dividing the 1.2 meter deep channel into 4 equal steps of 0.3 meters each. This allowed us to compute the capacity numerically and run an analytical check to prove our accuracy. So on this slide, I've combined our project objectives and our FILA table framework. Looking at our core objectives, we aim to identify the hydraulic variables of the drain, apply Simpson's 1/3 rule across 4 equal intervals to find the water area, estimate the peak flow capacity using Manning equation, and double-check our work against exact calculus to prove our method works. To keep our workflow organized, we map everything out into this FILA table. Under facts, we listed our physical channels data like the 2 meter bottom width and the 1.2 meter maximum wall height. Our ideas revolve around using numerical integration and Manning's equation to find the capacity. For learning issues, we focus on how to properly set up the step size and separate our coordinate nodes into the odd and even columns for the Simpson's formula. Finally, our actions included building the node table, calculating the final numerical area of 3.84 square meters, finding our peak flow of 8.14 cubic meters per second, and running the manual calculus check, which successfully gave us the perfect 0.00% error. Now that we've established our project baseline, I will hand over the presentation to my teammate who will walk you through the step-by-step calculation and data tables. Thank you.
Hello everyone, I will now present the literature review for our project focusing on how numerical mathematics optimize the urban drainage design. First, under the drainage flow capacity, open channel systems are vital for managing stormwater and preventing urban flash flood. We utilize the Manning equation to determine maximum discharge capacity, a calculation that strictly demands highly precise structural input for both the flood area and the weighted parameter. Next, regarding the limitation of standard formula, Traditional textbook geometry assume perfectly straight channel boundaries. In real-world engineering, concrete drains become irregular and non-linear due to the physical wear, soil-safe and uneven sediment build-up. To overcome this without making any wild guesses, we must implement the numerical method to break this unpredictable profile into a uniform depth interval h equal to zero point 0.3 meter. Finally, looking at our Simpson rule solution, we apply Simpson 1 over 3 rules to mathematically integrate the top with function. This numerical integration yields a highly reliable precise cross-sectional area of 3.84 meters squared. By putting the verified area into the main equation, we can confidently calculate the true maximum flow of 8.14 meter cube per second. Thank you.
Assalamualaikum and hi, my name is Nur Alifah Inshirah. I will present about the methodology of this project. The methodology of this project consists of four main stages. First, we define the geometry of the proposed trapezoidal concrete monsoon drain and develop the width function by equal to 2 plus 2y to represent the variation of channel width with water depth. Next, Simpson's 1 over 3 rule was applied by dividing the depth domain into four equal intervals with a step size of 0.3 meters. The width values at each node were then used to calculate the cross-sectional area of the channel. After obtaining the area, Manning's equation was used to determine the maximum discharge capacity Qmax of the drainage system. Finally, the numerical result was validated using analytical calculus and the percentage error was calculated to evaluate the accuracy of the method.
Hi, and now I will continue the presentation with the calculation. First of all, we must calculate the covering geometric equation with the formula area. For this project, we use the trapezoidal formula area, which is the area equal to B, which is the length of the weight. We use the 2 and 2zy. Y is the depth and Z is the ratio of the inclination of the side of the trapezoidal. In this project, we use 1, 1. After that, we put inside the integration formula with the 0 for the minimum depth and 1.2 is the maximum depth. And for the next procedure with discretization of the domain for the Simpson 1 over 3 grid. First of all, we calculate the area, the value of H, which is the Y max equal to Y initial and divide with N. Y max is 1.2 minus 0 and divide with N that we use for this project is 4. We get the 0.3 for the each H. And we put inside the table of the Simpson 1 over 3 grid. We calculate the total of the first and the last structure node, the odd interval node and even the interval node. And for the next procedure is the value of the total we put inside the formula of Simpson and we get the area is the 3.84 and we put aside the minor equation to calculate the maximum discharge and we get the 8.14 meter cube per second. And for the last procedure, we calculate the analytical validation and error analysis. We use the standard area for calculate the area exact and we get also 3.84. That means the percentage area that we get for this project is 0%. This means our calculation is correct. This occur because the channel boundary are perfect linear, allowing the second degree parabotic interpolation of the sensor formula to the map geometrically flawlessly. And now, I will pass it to the next presenter, Muhammad Ishraf.
Assalamualaikum and greetings audience. So I'm Ishraf. So I'm going to present for the discussion of our project. So for the discussion to solve this, we use numerical method divided into three logical steps. So that you can see here, there is four steps that we going to show all of you. So first, we define the physical geometry because the drain is wider at the top, so the water surface width changes continuously, and then we model this with the function by equal to plus 2y. So second, we perform the domain discretization. So we divide the 1.2 meter drain depth into four equal interval, giving us a step size of 0.3 meters. So using an even number of interval is a straight requirement for Simpson's 1 over 3 rule. So third, we evaluate the numerical integration. By the Simpson 1 over 3 rules, we calculate that the total cross-section area of the water is exactly 3.84 square meter. But what does this area mean for the real world? To find out, we pair our calculate area with Manning equation. So by factoring in the concrete's roughness, the weight parameter, and the channel slope, we calculate an ultimate discharge capacity of 8.40 cube meter per second. So in simple terms, this means the drain can safely transport about 8,140 liters of water every single second right before its overflow. So this is critical metrics for engineers to ensure the infrastructure can withstand Pariraja extreme rainfall and prevent flash flood. So to prove that our method is reliable, we perform on an error analysis. So we compare our numerical result with an exactly analytic calculus evaluation. So both methods produce the same exact of the area, which is 3.84 square meters. So this means our true percent relative error is exactly 0.00%. See, so this flawless accuracy happens because of our channel boundaries are perfectly linear, so allowing us the parabola in system rule to the map to shape perfectly without any deviation. So to conclude for this project, we are successfully demonstrate how numerical mathematics can solve real world urban hydrology and flood mitigation problems. So we have proof that the proposed monsoon drain in Parit Raja has a safe maximum capacity 8.14 cube meter per second. So furthermore, our project is 0.00% error validate that Simpson's 1 over 3 rules is highly precise. So making it a dependable substitute when standard formula fail. So ultimately, this project highlight the strong synergy between mathematical modeling and modern civil engineering. So this tool empower us to optimize drainage and build resilient flood-proof environment that protect our local community. Thank you for your attention for our